Hi everyone, in this video I'm gonna give a brief lecture on conservation of mass and solve some problems. So the conservation of mass says that the amount of mass in a system is constant, or the time rate of change of the system mass is equal to 0. And here the time rate is defined as the material derivative, where here the mass of the system is equal to the integral over the system of the multiplication of fluid density which is rho, and also the volume, which is shown with this curly V, and also the material derivative is defined as this equation, which has two terms. Here the first one is called the temporal derivative, and this term is called the convective derivative, where here this V is the vector of velocity of the flow. So now we have these two definitions. If we substitute these two into the conservation of mass equation, here we can find the conservation of mass. Here both the integrals are over the control volume, but we can change the second integral to be over the control surface, which will give us this equation. And this equation is known as the conservation of mass or continuity. And here the first term is the time rate of change of the mass. This rho dV is the mass. And here is the time rate of the change of the mass of the contents of the control volume. And here the second term is the net rate of flow of mass through the control volume surface, which here this term here is the flow of mass, the net rate of flow of mass through the control surface, and m dot is the mass flow rate, which has a dimension of kilogram over seconds. Rho is the density of the fluid and has the dimensions of kilogram over cubic meter, and V is the velocity vector, which has a dimension of meter over second, and A is the area, which has a dimension of squared meter. And also V dot N is the dot product of the vector of velocity, and N is normal to the surface. And V dot N is defined as the magnitude of the velocity vector times the magnitude of the normal to the surface times the cosine of theta, which is the angle. Theta is the angle between the two vectors V and N, where here N is equal to 1 because it's the unity vector normal to the surface, and the magnitude of the velocity vector is the square root of all different components of the velocity. So the first problem for the conservation of mass says that water flows steadily through the horizontal piping system shown in the figure. The velocity is uniform at section 1 here. And when it says uniform, it means that the magnitude of the velocity doesn't change with the position. It's the same in each position here. And the flow rate, the mass flow rate, at section 2 is given as 10 slugs per second, and also the area is given. And it says that the velocity is non-uniform at section 3. As you can see, the velocity changes with position, so it's non-uniform. In part A, it says determine the value of this quantity. And what is this quantity? This quantity is the continuity or the conservation of mass. So for this problem, first we need to define the control volume. And if the whole pipe with all three open surfaces is selected, so we can select this as our control volume. So on surface 1, water flows in, so it flows in steadily. And on surfaces 2 and 3, water goes out of the control volume in the same manner, which is steady. It means that it doesn't change with time. So we can conclude that for the selected control volume, this integration is equal to 0 because the mass is constant. Anything goes into the control volume at section 1 leaves at section 2 or 3. So there is no mass change inside the control volume, and rho is constant everywhere because everywhere the fluid is the same. So rho is constant, and also nothing changes with time. So d over dt will be equal to 0. And at part B, it says that determine the mean velocity at section 2 here. Here at section 2, we want to find the mean velocity. So we want to have the mean velocity at section 2. And we have the mass flow rate, which is equal to 10 slugs per second. And also we have the area there, which is equal to 0.3 square feet. And we know that the mass flow rate, or m dot, is equal to the multiplication of the fluid density, the velocity, and the area. So from here we can find the mean velocity at section 2, which is equal to m dot at section 2 divided by rho times the area. We have the value of m dot. It's given as 10 slugs over second. And also the fluid density for water is 1.94 slugs per cubic feet. And the area at point 2 is given as 0.3 square feet. So from here we can find the velocity, the mean velocity at section 2, which is 17.18. So in part C, it says determine, if possible, the value of this integral over section 3. If it's not possible, explain what additional information is needed to do so. So this integral is the second term in the conservation of mass. So we can write the conservation of mass again, which is del over del t, integral over the control volume, rho times the volume, plus integral over the control surface of rho v dot n dA is equal to 0. And since the flow is steady, del over del t is equal to 0 because of the steady flow. So now we can write this integration for different surfaces that we have. So this was our control volume, So this is the surface that we have as the control surface. So we need to write this for all the surfaces that we have. So here is surface number 1, here is surface number 2, and here is surface number 3. So we can write the integration for control surface for the surface number 1, rho v dot n for surface number 1, dA1, the area, plus the integration over the control surface number 2, rho, which is constant, v dot n at surface number 2 and the area there, plus the integral over the control surface, the third part, v dot n dA, plus we write one more term for these parts that are not numbered. So plus control surface, the rest of the control surface, rho v dot n of the rest and its area, and this will be equal to 0. So we have split this one single integration over the whole control surface to 4 different integrals, one for the surface number 1, one for surface number 2, one for surface number 3, and one for the rest of the surfaces. So here for the rest of the control surface we have this term, which is v dot n, and remember that v dot n, it was equal to the magnitude of v times the magnitude of n times the cosine of the angle. But here we know that this velocity is equal to 0 at these surfaces. At all these surfaces the velocity is 0. So this integral will be equal to 0. So this is 0. So we only need to write the integration over the surfaces that are either inlet or outlet. The value of rho for all of these 3 surfaces is the same, is the density of the water or the fluid, which is water here. So we need to find the dot product of the velocity and the normal to each surface. So v dot n for surface number 1 is equal to the magnitude of the velocity at surface number 1 times the magnitude of the unit normal to the surface times cosine of theta, the angle between these two. So here at surface number 2, the normal to the surface always points outward. So this will be n1. So since the velocity is to the right and normal to the surface is to the left, so the angle between these two vectors is equal to 180 degrees. And also the value of the magnitude of the unit vector here, n1, is equal to 1. So here this will be equal to the value of the magnitude of the velocity times the normal to the surface times cosine of 180 degrees, which this is equal to minus 1. So this will be equal to minus the magnitude of the velocity at the surface 1, which is 15. So this is v dot n for surface number 1, which is inlet. Then similarly we can do the same thing for surface number 2, which is the magnitude of the velocity at that surface times the unit vector, normal vector, times the cosine of the angle between these two vectors. So again here the velocity is outward, and also the normal to the surface is always pointing outward. So here for the outlet, the velocity is in the same direction as the normal to the surface, so the angle between these two vectors is equal to 0. So here we will have the magnitude of the velocity at surface number 2 times 1 times cosine of 0 degrees, where cosine of 0 degrees is equal to positive 1. So this will be equal to the velocity at point 2, which we found in section B, and it was equal to 17.18 feet over second. And this is outlet. And as you can see, for the inlet we had negative sign, and for the outlet we have positive sign, since the velocity and normal to the surface are in the same or opposite directions. Then also we can write the same thing for surface number 3. The magnitude of the velocity at surface number 3 and 3, and again cosine of theta between these two vectors, where again here the velocity is going to the right and it's in the same direction as the normal to the surface. So the theta is 0, cosine of theta is 1, and this will be equal to the velocity, the magnitude of the velocity vector at surface 3. So we want to find this one. We need to find that. This was the integral that we want to find the value for this. So the integral over that control surface rho v dot n dA is equal to, based on this continuity equation, this term was 0, and we can move these two terms to the right hand side and leave this term, which is unknown, in the left hand side. So this will be equal to minus on control surface 1 rho v dot n1 dA1 minus cs2 rho v dot n 2 dA2. So from here, on surface number 1, the area is constant and is given as 0.7 squared feet. So it will be equal to rho times v dot n, which we have it here as minus 15 feet per second, times the area at section 1, which is given here 0.7 square feet. This is the first term, and then for the second term we have a negative sign here, so minus rho v dot n at section 2, which we found it here as positive 17.18 feet per second, and also the area at section 2 here is given as 0.3 square feet, and also the area is 0.3 square feet. So here you can see that we can find the value of this integral, which is equal to this term. So for part C, it is possible to determine the value of this integral.